Hello everyone and welcome to your lesson of physics. Uh, this is a crash course that I've started, and in this one I'll be going through the very first chapter step by step, and also after going through the certain topics we'll be solving their sample question, past paper questions. So the first chapter I've divided into mainly two parts. The first one is all about physical quantities and measurements, and the second part would be about scalars and vectors. So in this video we'll be solving questions related to physical quantities and measurements. We'll be going through different measuring tools and from different instruments that can be used, and how do we use those instruments to measure a certain physical quantity, especially micrometer. Vernier calipers will not be studying in details because that has been removed from the syllabus. Once again, this course has been designed especially for the syllabus 2023 onward, 2023 to 2025. So all the students who are currently in O1, O2 or O3, this video would be compatible with your syllabus. Alright everyone, so this is the first thing. Now we have basic physical quantities, aka base quantities. So first of all, there are three primary colors: red, blue, green, and using those three primary colors you can get pretty much every color. Likewise is the case with quantities. So these 7 quantities, you can consider them the primary, just like the primary colors, because these are the quantities. By using a combination of these quantities you can get a whole lot of new physical quantities. So these 7, they're independent, they have their own definition, they do not depend on any other quantity to be defined, but at the same times you combine one or two or three of these quantities or even more, and they'll give rise to a lot of physical quantities. So these 7 base quantities are primary colors, just like primary colors, and more importantly, your syllabus, your objectives, they demand, the CIE, it demands that you should be aware of all these 7 physical quantity and you should have memorized it. So the first one that we have here is titled as time. All right, no need to memorize them in order. What you have to do is just memorize the name of the quantity along with the name of the unit and its symbol. So time, it can be represented, it can be measured in a lot of units, for example minutes, hours, and days, seconds, but the seconds is the standard one. So here in this column, in the last one, I have written the units, not the popular one or not just a random unit. This is the standard unit or the general unit. Technically we call it SI unit, System International Unit. So this is the unit that is the standard unit for the physical quantity written on the left side. So if we talk about time, it, like I said, can be measured in a lot of units, but second is the standard one. For length, it can be measured in a lot of units. Matter of fact, light year, that is also another unit, which is unit of length. And kilometers, meters, centimeter, millimeters, yard, feet. So all of these are units of length. And when I say length, it can be distance, it can be thickness, it can be width, it can be height, it can be displacement, can be anything like that. But the standard unit would be meters. Mass, amount of substance, the standard unit is kilogram. So electric current, ampere, thermodynamic temperature, which is represented by T and sometimes also represented by theta, it is measured in Kelvin. Other units are degree Celsius, degree Fahrenheit, but the standard one is Kelvin. Amount of substance, in chemistry we have a full chapter dedicated to it. It's measured in moles. Luminous intensity, it is measured in candela. Luminous intensity means intensity of light. It is measured in candela. We don't have to do much with the last one in our physics syllabus, but the starting ones, they'll be used plenty of times. Let's move on to the next thing, length measuring instruments. Alright, so we're starting with the length measuring instruments, and basically in our syllabus we have generally they ask us about questions from these 5 length measuring instruments, and I've written them in order in the decreasing order of their range. The first one at the top, trundle wheel, it has the highest range. When I say the word highest range, it means it can be used to measure long lengths, like very large distances. And screw gauge, or called screw gauge as well, it is used to measure very small objects. So the range is not important, but precision is more important for the ones at the bottom. So let's talk about trundle wheel. If I talk about the range of it, it can be used to measure distances that are several meters, and generally from anywhere between 50 to 1000 meters. We easily use trundle wheel. We easily prefer trundle wheel to measure these kind of distances. For example, there are civil engineers, they want to construct a football field, and they want to measure the distance of the football field. They can use the trundle wheel. Tape measure, all right, it is used to measure the distances like around 50 to 60 meters at a maximum of like 60 meters. All right, if we have to measure length that is like maximum 50 to 60 meters, we would prefer tape measure. So 10 meters needs to be measured, 20 meters, 30 meter, 40, 50, 60. We can easily go with the tape measure, but if the distance exceeds that, then we prefer trundle wheel. Once again, the range of tape measure, it varies because it does not come in a single variety. It does not come like in a single type. It has plenty of types. It is also custom made as well for different purposes, so its range kind of varies. The next one that we have is meter rule, that we generally use in our science labs as well, and it is used to measure objects that are maximum of 1 meter, that is equivalent to 100 centimeters. All right, so anything that is within 100 centimeter mark can be measured by using meter rule. Then we have calipers and the screw gauge. All right, screw gauge, these two instruments, they are not like in these two, range is not really important. We don't worry about the range because their sole purpose is to go for the precision, to measure accurately to like a lot of decimal places. So we don't really measure big objects with it. We measure small objects, for example, thickness of a wire, or length of, or circumference or diameter of a sphere, small sphere, or a metal ball. These kind of objects can be measured by using calipers and screw gauge. So this one, vernier calipers, we can measure a maximum of the ranges, right, approximately 15 centimeter. All right, when we use the word range, it is already obvious that we are referring to the maximum value. Alright, so I don't even need to write maximum here. This is just for the sake of understanding. I've written maximum. But when you say the word range, like what is the range of this thing, it itself means what is the maximum thing, or what is the maximum value that it can cover up, or it can measure. Now for the screw gauge, the maximum is 6 to 8 centimeters. So once again, it's used for very small, to measure very small objects. All right, the next thing is we have here is precision. Now one thing should be clear, that precision and range, they go against each other. Generally they go against each other, because if you are referring to an object or an instrument that has a high range, very high range, so generally, with few exceptions, generally its precision would be little, if precision would be low. And high precision means it can measure very small objects, it can measure with very high accuracy. And this word least count here, that is very important. So least count is the smallest reading that can be measured accurately with an instrument, the smallest reading. So sometimes range is not important, rather we have to go for precision. We have to use an instrument that would give us a very precise, very accurate value. All right, at this stage, precision and accuracy we consider the same thing at this stage, but in A levels, yeah, we learn that these two are slightly different. They have a difference, a specific difference, but right now you can think of precision and as accuracy as well. So the more the decimal places as an instrument gives, the more precise it is, and the more will be the least count. For example, I get a reading that is 0.12 seconds, all right, and I get a reading that is 0.1 second. So the reading obtained from the first stopwatch, let's say, is more precise compared to the second reading. Why? Because the first reading gives me more decimal places. So the least count once again refers to the minimum value that can be measured by an instrument. If we talk about the trundle wheel, its precision or least count is, for some of the trundle wheels it is 1 centimeter, and for some of them it is 0.1 centimeter. So 1 centimeter or 1 millimeter, you can call it that way. For the tape measure, its precision, or the lowest reading or the minimum reading that you can measure with the tape measure is 0.1 centimeter, or in millimeters that equals 1 millimeter. Right, this is the lowest reading that can be measured by the tape measure or measuring tape. Then the next one we have is meter rule. So meter rule has the same precision. It can also measure a minimum of 1 centimeter accurately, or in 1 centimeter corresponds to 0.1 centimeter corresponds to 1 millimeter. Vernier caliper is more precise. Matter of fact, it is 10 times as precise as the meter rule. So its least count is 0.01 centimeter, or yeah, in millimeters that is 0.1 millimeter. If we talk about the screw gauge, it is 10 times more precise, more you can say it is 10 times more precise than the vernier calipers, and hence its least count is 0.01 centimeter, or in millimeters that would be 0.01, 0.01 millimeters. Applications, our trundle wheel, we use it to measure length of tracks, or long tracks, or long distances, long lengths. Tape measure, uh, tape measure and meter rule can be used interchangeably, but the thing that is specially associated with tape measure is it can be used to measure curved lengths. Alright, so for example, you have a ball that looks like this, alright, or you have a tennis ball. You want to measure the circumference of the tennis ball, like to start from here and take a measurement all the way around till the starting point. What do we use? We cannot use the meter rule because meter rule is flat, it cannot be curved, but tape measure can be curved. So tape measure and meter rule can be used interchangeably, but if the surface is curved, then we prefer tape measure. So meter rule, flat surfaces. Once again, there are approximately 100 centimeter or less than that. All right, if it is more than that, then we would prefer tape measure. All right, even if it's a flat, let's say this is a flat surface and the length is 160 centimeter. All right, somewhere between 160 to, let's say, 200 meters. We're not sure we want to measure the exact value. We'll prefer the tape measure, right? Because tape measure has a higher range. All right, then we talk about the vernier calipers. And for the vernier calipers, the thing is that it can be used for measuring internal and external diameters of anything, or can be of a pipe, can be of a hollow bottle or something like this, and also it can be used to measure depth of liquid. Right, it has a kind of a needle that sticks out from the backside. We dip it in the water or any liquid whose depth needs to be measured, and the reading of the depth would be displayed on the scale. Then we have the screw gauge. It is generally used to measure very small objects. What kind of objects? For example, thickness of a wire, thickness of like 4 to 5 sheets of paper. Objects of very small length, very small diameters are generally measured with the micrometer screw gauge. Screw gauge also, it is known as micrometer, right? Sometimes they simply use the word micrometer. So when they say micrometer, it should be obvious that they are referring to the screw gauge. All right, so now we're going to see how we can use micrometer or screw gauge to measure thickness of an object. Once again, micrometer, it is an object that is used to measure very small lengths or very small. When I say the word lengths, it can be anything. It can be distance, it can be thickness, it can be diameter, or anything with the unit meter, centimeter, or millimeter. So first of all, the thing about the least count is the least count of this instrument is 0.01 millimeter. All right, that's the least count. What do we mean by that? What we mean is it can measure a minimum of 0.01 millimeters accurately. anything that is smaller than that, let's say we have a wire which is not even 0 point, or we have sheet of paper, 2 or 3 papers whose thickness is not even 0.01 millimeters, so we cannot accurately measure that one. So it can accurately measure up till 100th part of a millimeter, not lower than that. So any reading that would fall below 100th part of the millimeter, that cannot be accurately measured. All right, let's think about it. Let's look at that. First of all, the structure of it. And the thing about the structure of it is it consists of 2 scales. All right, this one is called main scale, and this one over here, this one scale is called circular scale, because it is kind of it is in a circular shape. So main scale and circular scale. All right, these are the important parts. It has a lot of parts, like there's a lock here as well, but this is not important for us because we need to refer to the portion that is used for measurement only. So in this position, when the lock is in this position, it is unlocked. All right, so before we take a reading, we need to make sure your micrometer is unlocked. All right, now how do we take the reading? First of all, it has 3 steps. First step is you need to take reading from main scale. I'm just writing it down here, then I'll show you how do we actually take the reading. Main scale reading, main scale R. Then we need to find the line coinciding main scale, then circular scale reading, circular scale R, and then final reading. All right, so first of all, let us see, or let us find out the reading on the main scale. All right, so this portion, this scale that you can see over here is called main scale. Now, how do we measure the reading on the main scale? First of all, this line, they have mentioned this line represents 0. All right, then the line next to it over here represents 1. So this one represents 1, and the next line represents 2 millimeters. All right, this main scale is in millimeters, like this. So the lower line between 0 and 1, it would represent 0.5. And the lower line between 1 and 2 represent 1.5. Right, these are the things that we should be aware of. Now, we have to look for how much distance or how many lines are being covered on the main scale, like till this point. How many lines or how much distance is covered on the main scale? You see 0, 1, 1.5, 2. We can see till line number 2 from the main scale. So we can safely write that the reading from the main scale is 2 millimeters. Reading from the main scale is 2 millimeters. So we write 2 millimeters here. This is the reading that we got from the main scale. All right. After you have gotten the reading, now you need to look for the reading of the circular scale. And before you start that, you need to find out that this is your central line. You have to look for the line from this circular scale that is matching with the central line of the main scale. I repeat, the line of a circular scale that is matching or that is coinciding with the central line of the main scale. Now in this case, it is line number 20, 21, 22, 23, and then 24. The line number 24 is the one that is exactly aligned with the central line of the main scale. So now we know that it is line number 24. So we can write it over here. It is line number 24. In the next step, in order to convert this line number into a circular scale reading, just multiply this line number with the least count of the vernier calipers. And like I said, the least count of this instrument is 0.01 millimeters. Now this line number would be converted into main circular scale reading, and it would be 0.24 millimeters. All right, so it is, that's not too much visible, 0.24 millimeters. Matter of fact, when you're advanced enough, when you're done enough practice, you can do this step in your mind. Like, soon as you know it is line number 10, after multiplying it would be 0.24. If it is line number 10, it would be 0.10. If it is line number 15, it would be 0.15. If it is line number 35, aligned with the center line of the main scale, would be 0.35. If it is line number 5, it would be 0.05, because you multiply 5 by 0.01, you get 0.05. All right, so that is the reading from the circular scale. In the next step, what we have to do is add the main scale reading, 2 millimeters, with the circular scale reading. So 2 plus 0.24, that gives us 2.24 millimeters. All right, so that would be the final reading from your screw gauge or from your micrometer. All right, another thing is, in this case we are assuming something, and we are assuming that there's no zero error in the micrometer. All right, what is zero error? How do we deal with that? How do we correct the zero error? How do we fix it? These questions would be answered later when we study zero error, and then we'll study how do we get rid of it. And we also study the types of zero error for the micrometer. All right, so here's another sample question with it. In exams, what kind of question do you get? Well, in the question you'll be given with a figure of the reading that is being measured using a screw gauge, and you'll have to find out what is the exact reading in number, or what is the diameter of the wire that is being measured by the micrometer. So this kind of situation would be given, and you'll be asked to find the reading. All right, so let's talk about this one. The first step that I told was you have to find the reading from the main scale. So we zoom it in and we try to find out how many lines of main scale have been covered till this point, till the circular scale. So this one is 0, this is 1, this is 2, this is 3, this is 4. It does not stop at 4, it goes till 4.5, because I told you the lower line at the bottom that represents 0.5, so it is 4.5. From main scale we have reading 4.5 millimeters, so you can write over here 4.5 millimeters. That is the reading from main scale reading. All right, now we try to find out the line of the circular scale that is aligned with the central line of the main scale. So this one is 30, the one above it would be 31, then 32, then 33, then 34, only then we can get 35 here. So it is line number 33 that is aligned with the central line of the main scale. You can see over here, line number 33 is aligned with the central line of the main scale, and once you multiply it by the least count, like I said, line number 33 you multiply by the least count, then you get 0.33, and in the next step millimeters, and in the next step you add these two values, and you'll be getting 4.83 millimeters. So this is how we measure reading using micrometer screw gauge. There's another one. Let's zoom it in. Once again, we'll try to narrow down the steps. First of all, quickly measure the reading from the main scale. How many lines are covered from the main scale till this point? It is 10, 10.5 from the bottom, and line number 11 is also covered. All right, so we write 11 millimeters we got from the main scale. All right, main scale reading was 11. Then we look for the line number of the circular scale that is aligned with the central line of the main scale, and it is straight away line number 0. So 0, you then multiply by the least count, and obviously it would be 0 once again. So we write 0 here, 0 millimeters plus 11 millimeters. You add these two. This one was the circular scale reading. You add these two, you get 11 millimeters. All right, but the better way is to write it as 11.00 meter. All right, but at your level, even 11 meter would be considered okay. Once again, the better way is 11.00 because we know that your micrometer is capable of measuring two decimal places in millimeters. All right, because the least count, once again, least count was 0.01. So we have written 0.00 because we don't want to give an impression that we were not able to measure the reading after that. We want to specify, yeah, we were able to measure the reading to two decimal places, but the thing is that reading was 0. All right, so once again, at your stage and O levels, 11 would be acceptable, but the better way would be to write 11.00. Let's crack this one real quick. So here we have another one, 5, 6, 7, 8, 9. 9 millimeter from main scale. All right, I hope that makes sense because this is line number 6, 7, 8, and 9 here. So 9 from there, and then we have 1, 2, 3, line number 3. All right, line number 3 from the circular scale, we convert it into the circular scale reading by multiplying by the least count, and that would be 0.03 millimeters. All right, and then you add these two, 0.03 millimeters added with 9 millimeters, that gives you 9.03 millimeters. All right, so the next thing that we're going to look at is what if the micrometer has a zero error in that. All right, in that case, you'll be asked to do a couple of extra steps in order to get rid of the zero error, or in order to compensate for the zero error, or in order to fix the zero error, so that even if there is zero error in your instrument but the final reading is unaffected, or the zero error is compensated uh, in a different way. Now, first thing is we need to understand zero error. What is the zero error? For example, you go to any supermarket and they are measuring a bag of rice that weighs approximately 2 kgs, whose mass is 2 kilograms, but you try to ensure that the mass is 2 kilograms, so they put it on the electronic balance. The first thing that you'll need to notice is the scale should start from 0. Right, otherwise we'll argue that why is it not starting, why is it already showing some number, or why is it showing a mass of 0.02 grams even if we have not placed any mass. Or when you go to the petrol pump, gas station, and before they start putting the fuel in, we need to ensure that the fuel or the meter that starts from zero, right? If it is not starting from zero, if there is fuel already, if there's some number already, or even let's say 0.01, then that means the reading is not starting from zero, and the quantity that you're getting would be measured inaccurately. All right, so the number that is displayed on the screen of the instrument would be indifferent from the actual reading or the actual quantity of that object. So in simple words, zero error, we define it on if an object shows a reading, shows a non-zero reading, when no measurement is being taken. So this is how we define zero error for all the instruments. All right, so if you're not taking any measurement, there's no object, there's no physical quantity that we are measuring right now, then the reading on the tool, on the measuring tool, should be zero. If it's not zero, then there is zero error. If it is zero, then there's no zero error. As you can see in the diagram, there's nothing that is placed on the electronic balance, still the reading is 0.02 grams. What effect do you think this will have on all the readings? The effect would be, let's say you need to get 1 grams, so it is already showing that even if they have not placed anything on it, you already have 0.202 grams. So in other words, you'll be getting less amount and you'll be paying for more physical quantity, for more yeah, or I can say that you'll be paying more than you should for, or in that case. So here is another example of zero error. All right, in this case, you see, this is a spring balance. When there's nothing attached with the spring balance, the reading is zero, as it should be. But in this one, when there is nothing attached with the spring balance, the reading is 0, 1, 2, 3, the reading is 1. So that means there is zero error in your spring balance, because if there is nothing attached, then it should be zero. It should be displaying zero. So this one, spring balance, has the zero error, and the one on the left has no zero error. Now zero error in the micrometer. How do we define zero error in the micrometer? Now first of all, like I said, micrometer has two scales, main scale and the other one was circular scale. This one was circular scale. On closing the micrometer, you're not putting anything in the micrometer, you're not measuring anything with it, you have just closed the jaws. All right, on closing the micrometer, if the two zeros are aligned with each other, then there's no zero error. No zero error. if the two zeros are aligned with each other. If you have closed the micrometer, not measuring anything, but the two zeros on closing the micrometer, the two zeros are not aligned, it does have a zero error. All right, then the thing is, in that way, if the zeros are not aligned, it gives us two possible conditions. First is the zero of the circular scale, the zero of the this one circular scale can be below the zero of main scale, or the other case is the zero of the circular scale can be above the zero of the main scale. All right, so once again, this one is circular scale and this side is the main scale. So if the circular scale is below, circular scale is zero is below the zero of the main scale, it has the zero error, or even if it is above the zero of the main scale, it still has the zero error. So these two types are classified as positive and negative zero error. Matter of fact, if the zero of the circular scale is below the zero of the main scale, then that way we call it positive zero error. So I can say, like in this case, the zero error is positive. Why? Because the zero of the circular scale is below the zero of the main scale. The other case is negative zero error. If the zero of the circular scale, right, this one was the zero line of the circular scale, is above the zero of the main scale, then that is negative zero error. All right, so this one was to how do we differentiate between negative and positive zero error in the case of micrometer. Then the next question is, all right, we know that there's zero error, positive or negative, but how much zero error is there? How much exactly, like in number, how much zero error is there? Now, in order to find that one, you need to find how many lines. For example, for positive zero error, you need to find out how many lines, or yeah, how many lines the zero error is below the zero of the main scale. Or in simple words, what you can do is that, all right, we know that line 0, this line of the circular scale is not aligned with the zero of the main scale, then you simply find out which line number is matching. So 1, 2, 3, or we see the zero is actually 3 places lower than it actually should be. It is 3 places lower, it is 3 lines lower. So you have the line number 3, you multiply it by the least count, 0.01, and then you get the zero error 0.03 millimeter. So this is a zero error that you get, 0.03 in this case. Same is the case for the negative zero error. All right, in this one what we do is we look for how many places or how many lines the circular scale 0 is above the center line. So it is 1, 2. The 0 of the circular scale is 2 lines above than it should be. Ideally it should be here. In order for no zero error, it should be here, but it is 2 lines above. So we write down that line number, we multiply it by the least count, and we write it down, we calculate it 0.02, but since this is the negative zero error, so we write down the negative sign. So this is the negative zero error. Now we have learned first of all what the zero error is, then we saw what are the two types of zero error in the micrometer, And how do we define zero error in the micrometer? What are the two types of zero error in the micrometer? And to find the exact value of zero error in the micrometer, like how much zero error it is. Now the final thing is, how do we compensate for the zero error? All right, so I'm going to assume, right, I'm going to raise it off for a moment, this one as well. So let us suppose that I have taken a measurement using the two micrometers, and the value that I obtained was 10 point, let's say 25 millimeters. All right, since micrometer can measure till 2 decimal places in a millimeter, so that makes sense. It is a supposed value. All right, it is a reading that I have measured with these faulty micrometers. When I say the word faulty, I say it because they were having the zero error in it. Right, now the next thing, so this reading, I can call it faulty reading. This is your faulty reading. This is your faulty reading. All right, so let us try to fix this reading from the zero error. In the first case, we know that the zero error was plus 0.03. So what you have to do is simply write down the faulty reading. This is the reading that is there, including the positive zero error. Then you subtract the zero error that you calculated, and I told you how to calculate that. You subtract these two, then the value that you get now would be the actual value, 10.22 millimeters. Now this is the actual value of the object, 10.22. So what we do is, in case of zero error, we subtract the amount of zero error from the faulty reading, and then that is your final accurate reading. All right, so there was zero error. We did not got rid of the zero error, but we done some mathematical correction in that, and we compensated for the zero error. Now for the negative zero error, so let's say I measured with the micrometer that was having negative zero error in it, and it was negative 0.02 millimeters, and the faulty reading, let's say, was once again the same, 10.25 millimeters. This one is a faulty reading, it has zero error in it. In order to compensate for the negative zero error, you simply add the negative zero error in it, and what you get is 10.27 millimeters. That would be your final reading. The thing is, in both cases we actually subtract the zero error, but for the negative one we subtract the negative reading, and it would be automatically plus. So actually it is like this.